Okay, so let's look at how we should be going about solving these related rates problems. So let's just read through this really quick. So we use principles of problem solving when solving related rates. So the steps are followed as follows. So always with word problems, it's reading the problem carefully. A lot of times you have to read through it a couple times and you're going to start pulling out information that you know. So read the problem carefully and write down all the given information. It's helpful, especially with these, to sketch and label a graph or diagram. Sometimes you're given those pictures, but a lot of times you're not. Then we need to find an equation that relates the unknown variable and known variables by looking at either geometric shapes, known formulas, ratios such as Pythagoras Theorem. So if we're dealing with a right triangle, area of volume formulas, maybe trig identities, but we need to relate these equations somehow together. And we want to simplify using appropriate substitution. So choose an equation only has two variables, the known and unknown. Once we've figured out that equation and related it, we're going to differentiate the equation on both sides implicitly with respect to time. So that was where each time we took the derivative of that variable, we had to tack on that d, whatever that variable was, all over dt. And then once we've differentiated, use implicit differentiation on both sides, you're going to go back in and substitute all the values into the derivative and solve for that final answer. Okay, so those are the steps that we're going to go through in order to solve these application problems. So first example, let's say that a boat is leaking oil and the radius is growing at a rate of 3 feet per second. How fast, I'm just going to read through it first. How fast is the area increasing when the radius of the oil spill is 30 feet? Okay. So we have a boat that's leaking oil. And the radius is growing at a rate of 3 feet per second. How fast is the area increasing when the radius of the oil is 30 feet? Okay, so we have this boat, it's leaking oil, and it's basically a circle that's growing, right? It's extending and extending. And so we know we have a circle. We know the area of a circle. It's pi r squared. We have a bit of information in here. Okay, so we are saying that the radius is growing at a rate. So that tells me right there, that's the derivative of 3 feet per second. So I know dr dt is equal to 3 feet per second. And we want to know what is the radius, or what is how fast. So we're looking for rate of change. We want to find the rate of change of the area, so dA dt. When x is equal to, or our radius, sorry, is equal to 30 feet. So we want to take the derivative, implicit differentiate both sides. So the derivative of the area, dA dt, this is equal to, so taking the derivative of pi r squared. Well, pi is just a number, a coefficient in front. So bring down our 2. We got 2 pi r. And r is with respect to time. And so we have to tack on this dr dt. So now all we're going to do is we're going to go back in here and we're going to substitute in what we know. We know what dr dt is at that time at 30 feet. So dA dt, this is equal to 2 times pi times r, which is 30, all times the rate of change of r, which is 3. So 2 times 30 is 60, 60 times 3, that's 180. So dA dt is equal to 180 pi feet squared per minute. So the area is increasing at 180 pi feet squared per minute. So you could always multiply that by pi if you want to get an estimate. You can leave it like that. Okay, so next type of example, we are given that a rocket is being launched. You are televising the launch. The camera needs to follow the rocket as it rises. The rocket is climbing at a rate of 600 feet per second. At 4,000 feet, how fast will the angle of elevation change to keep up with a rocket at 4,000 feet? Okay, and you're also given that you're 3,000 feet away from the launch pad. Okay, so rocket launch. We want the rate of change the angle rate of change of the angle. So maybe we could call that d theta dt. Rocket's climbing at a rate of 600 feet per second. So the rocket climbs at 600 feet per second. Okay, so this is a rate of change. We can think of this as our height. So our height is changing. So rate of change It's derivative. So dh dt here, we know is equal to 600 feet per second. We want to know how fast will the angle of elevation change when we reach 4,000 feet. So we want this rate of change of our angle when h of t is equal to 4,000 feet. And we're given that you are standing 3,000 feet away from this, where the rocket was launched. So the rocket is going upwards. And we want to know what this angle, because this angle is changing as this rises, when this is 4,000 feet. Okay, so looking at this, I'm looking at my angle and I'm looking at how it's changing. I'm looking at what I know. And this is h of t, really, but we want to know when it's 4,000 feet. Looking at this and what I need to use, I have h of t and 3,000. And I know that my angle that deals with, if I put theta here where I'm at, opposite and adjacent is tangent. So I know that tangent theta is equal to my opposite side over my adjacent side. So my tangent theta, this is equal to opposite, which is the height, all over the adjacent side, which is always going to stay the same, 3,000 feet. So we want to use implicit differentiation here. Just tied our formulas together, what we know. And so let's take the derivative on both sides. So looking at the derivative of tangent theta, remember theta is changing with time, so we have to use implicit differentiation, the chain rule. The derivative of tangent, that is secant theta, secant squared theta, times d theta dt. The rate of change of that angle at time t is equal to, so the derivative of h, so that would be h prime of t. Actually, it's just gh dt. You can think of this as 1 over 3,000, which is just a coefficient in front. And now we want to go in and we want to plug in stuff. We're trying to find the rate of change of our angle. Let's just go ahead and put in what we know. So we have secant squared theta, or maybe secant squared theta, times d theta dt, which is actually what we're trying to solve. I'm going to put that in a different color, is equal to 1 over 3,000 times dh dt. So we know what dh dt is, which is 600. So I can change this, or I can simplify this. Let's solve for d theta dt. Well, actually, let's simplify first. So we have secant squared theta times d theta dt is equal to, so right-hand side, 600 all over 3,000. So 100 goes into both of those, 6 over 30, that's going to reduce down to 1/5. So I can divide both sides by secant squared theta. So I would get then my d theta dt is equal to, or I can think of it as multiplying by 1 over secant squared theta. So this would be 1 over 5. And I'm going to rewrite secant squared theta as secant theta quantity squared. So I need to figure out what secant theta is. And I could figure out what secant theta is by looking at my trig identities. Secant I know is 1 over cosine. So if I did that and kept it as cosine, I guess I don't have to. So this is equal to 1 over 5, 1 over cosine theta, quantity squared. Well, cosine theta, how can we figure that out? Cosine theta is opposite. It's not opposite, it's adjacent over hypotenuse. I know what my adjacent side is. I need to figure out what my hypotenuse is. We know what the height is. It's going to be 4,000 here. And so 4,000 is our height. And I know that this is 3,000. And so I can use that to figure out what this length is at 4,000. And so I need to use my Pythagorean theorem. So my hypotenuse squared is equal to 3,000 squared plus 4,000 squared. So doing that, I get 3,000 squared is going to have 6 zeros. Plus 4,000, 6 zeros. If I add those together, that gives me 25. Million. Take the square root. I get 5,000. So cosine of theta, when I redo this, this is equal to 1 all over 5, 1 over cosine theta, which is adjacent over hypotenuse, or hypotenuse over adjacent for a secant. So hypotenuse over adjacent would be 5,000 all over 3,000 quantity squared. So reduce down. So I have 5/3 quantity squared. 5/3 quantity squared is 25/9. So this is 1 over 125 divided by 9. And we get d theta dt is equal to 9 divided by 25. do something wrong. Just look at this one again. Sorry, I'm going to pause it for a sec. Okay, so I do have everything right, but this is the rate of change. We are in terms of radians. So this is radians per second. So it really depends if they wanted the number of degrees. Remember that degrees we would multiply by 180 over pi. So the rate of change and we can plug that in. So 9 times 180, that's going to give us 1,620 all over 25 pi divided by and this is going to be approximately 20.6 degrees per second. So the rate of change when that rocket is hitting 4,000 feet, that rate of change of the angle is changing right there at 20.6 degrees per second.